In the third part of thermal physics, we have to discuss Maxwell's distribution of velocity. We know that gas molecules are moving with the different velocities at different places. After each collision, their velocity can be changed. Some molecules may move with the velocity greater than the root mean square velocity, and some other molecules may move with a velocity less than the root mean square velocity. According to Maxwell-Boltzmann distribution, the number of particles occupying a particular state is given by the formula n equal to G divided by e power alpha plus beta into ei. Then this is modified as j into e power minus alpha into e power minus beta into ei. Now we have to find out the value of ei using the formula half mv square, that is kinetic energy. If m is the mass of the molecule and v is its velocity, then momentum p equal to mv. Then ei equal to half mv square is equal to m square v square by 2m. Just we have multiplied this numerator by m and the denominator also by m. M into v is p, so this is p square divided by 2m. Now this equation is modified in this form. We may rearrange this equation in this form. N of p equal to g of p into e power minus alpha into e power minus beta p square by 2m. N of p gives the number of molecules in unit momentum interval between p minus 1 by 2 and p plus 1 by 2. And g of p gives the number of cells in the phase space corresponding to this momentum interval. The number of molecules in the momentum interval between p and p plus dp is obtained just multiplying both sides of this equation by dp. So this is the equation. Now we have to find out the value of g of p into dp. G of p into dp equal to volume of phase space containing to the momentum interval p and p plus dp divided by h cube. This is volume of the phase space. Volume of phase space corresponding to momentum interval p and p plus dp is equal to integral dx dy dz into integral dpx dpy dpz. This is position phase, this is momentum phase. These two are called as phase space. We know that volume of phase space is h cube, which is obtained by the formula delta x delta y delta z into delta px delta py delta pz. We know that delta x into delta px, the product of error in position and momentum, is equal to h, almost equal to Planck's constant. So in this manner, if you combine these two things, you can get another one h. If you combine these two things, you can get another one h, so that the volume of phase space is h cube. We can arrive this. Now, integral dx dy dz is equal to v, that is volume in position phase. So g of p into dp equal to, instead of this we have to put v, take this h cube outside, integral dpx dpy dpz. Now we have to evaluate this integral. The value of the integral is 4 pi p square into dp. Now the value of g of p into dp becomes 4 pi p square dp into v divided by h cube. Then n of p into dp equal to 4 pi v p square by h cube e power minus alpha e power minus beta p square by 2m into dp. The value of e power minus alpha is n h cube by v into beta divided by 2 pi m power 3 by 2. Now n of p into dp is presented in this form. Just h cube cancelled out, VV cancelled out, then we can get this relation. In the above relation, put beta equal to 1 by kt. Now, Maxwell-Boltzmann law of distribution of momentum is 4 pi n 1 divided by 2 pi m kt entire power 3 by 2 p square e power minus p square by 2 m kt into dp. The above equation gives the number of molecules having momenta between p and p plus dp. Maxwell-Boltzmann law of distribution of velocities is obtained by replacing p by mv and dp using m into dv in the above expression. Here n of v into dv equal to 4 pi n 1 divided by 2 pi m kt power 3 by 2. Instead of this p square, we have to write m square v square. Then e power, instead of this p square, put this negative sign as such, m square v square divided by 2m into kt. Then dp is m into dv. Now, this m square and m. This m square and m are tailored. Then this is my e power minus m v square divided by 2 pi kt. This m square into m is m cube. Then this m cube divided by m power 3 by 2 is m power 3 by 2. So this equation is modified in this form. Now, you may say this relation gives the number of molecules having velocities between v and v plus dv, and is known as Maxwell-Boltzmann law of distribution of molecular velocities. Then we may go to the concept of average velocity. Velocity of all the molecules is integral v into n of v dv, a limit varying from 0 to infinity, because the molecules are moving with velocities between 0 and infinity. Then total number of molecules is given by this formula. So v bar is equal to this much. Finally, we may get the value of v bar equal to root of 8 into kt divided by pi m, which is equal to 1.59 into root of kt by m. Root 8 value is 1.59. Then RMS velocity, that is root mean square velocity value, is root of 3 kt by m. Sometimes we may call this one as c bar or vrms, crms, any notation you can use, which is equal to 1.73 into root of kt by m. Then most probable velocity is root 2 kt by m. The value of root 2 is 1.41 into 1.41 root 2 value, then 1.41 into root of kt by m. If you arrange the velocities, they are in this order. V RMS is greater than V average is greater than most probable velocity. If you see this curve, the area under the curve represents the molecules which are having velocities between 0 and infinity. If V equal to 0, suppose the molecule velocity is 0, then n of V is 0. That is, the molecules of 0 velocity are not possible. The probability of getting a molecule with 0 velocity is impossible, because all the molecules are making their random motion. The shaded region of the curve represents the number of molecules of the gas between the region, between the velocity v and v plus dv. That means the region between v and v plus dv. The number of molecules having very high and very low velocities is very small in the gas. The curve is asymmetrical. The velocity corresponding to the peak of the curve, so this point x equal to 1, is known as most probable velocity. See, if you make a dotted line here, which may provide the number of particles. So most of the particles are having a particular velocity. Such velocity is called as most probable velocity. Then we may go to the next topic, atomicity of a gas, alpha. The number of atoms in a molecule determines the atomicity of a gas. Alpha atomicity equal to increase in total energy divided by increase in translational energy. If you consider a molecule which has translation energy, rotation energy, vibration energy, like that. Increase in total energy of the gas is given by the formula Cv into dt. Here Cv is the specific capacity at constant volume. You know that Cv equal to du by dt. So du equal to Cv into dt. Average kinetic energy of translation of a single molecule is 3 by 2 into kT. You know that energy associated with each degrees of freedom is U equal to half kT. Here the molecule is subjected to move along x, y and z direction. So for a single molecule, the translational kinetic energy is 3 by 2 into kT. The increase in translation energy of 1 mole of the gas. 1 mole contains n number of molecules, that is Avogadro number, n equal to 6.023 into 10 power 23. So 3 by 2 k, this t is replaced by dt into n. But r by n equal to k. So n into k is r. R is our universal gas constant. So the above relation is modified as 3 by 2 r into dt. Now alpha equal to Cv into dt. Increase in total energy is Cv into dt. Increase in translation energy is 3 by 2 r into dt. So this is 2 by 3 Cv by r. Dt cancelled. But according to Mayer's relation, Cp minus Cv equal to r. So this r is replaced by Cp minus Cv. Now this is modified as 2 by 3 Cv by Cv1. Cp by Cv is our gamma minus C by Cv1. So that we can get this relation. Then alpha equal to 2 by 3 into 1 divided by gamma minus 1 is the relation connecting atomicity and Cp and Cv. For a monatomic gas, you know that only translation motion is possible for monatomic gas. No talk about rotational motion. We have to prove the same. For a monatomic gas, gamma equal to 5 by 3, the value of gamma. Then instead of gamma, if you put 5 by 3, we can get 1. Because 5 minus 3 whole divided by 3. 5 minus 3 is 2, then 3 by 2. 3 cancel out, 2 cancel out, 1. It means that the total energy is equal to translation energy of the molecule, because alpha, atomicity of the gas, is increase in total energy divided by increase in translation energy. Here we are getting the value of 1 for monatomic gas. So the total energy equal to translational energy. That means no talk about rotational or vibration energy. In the case of monatomic gas, the molecules do not possess rotational or vibration energy. They are having only translation energy, because the value of atomicity is unity. For diatomic gases like oxygen, nitrogen, etc., the value of gamma is 7 by 5. Therefore, the value of alpha is 5 by 3. It shows that the internal energy of the molecules in diatomic gases is 2/3 of the translation energy. Smaller is the value of gamma, greater is the atomicity of the gas.